All right, let's do problem 41 on page 269 in chapter 11. Here's the problem. Let's see. It says, in the 1950s, an experimental train that had a mass of 2.5 times 10 to the 4 kilograms was powered across a level track by a jet engine that produced a thrust of 50,000 newtons for a distance of 509 meters. Find the work done on the train, find the change in kinetic energy, find the final kinetic energy of the train if it started from rest, find the final speed of the train if there were no friction. Okay, so let's do given. I think I can get this done. Given. Okay, we got a train. Here's the track. Here's the train. I don't know. You got to have a smokestack on it. And here's the boiler, the cow catcher, the boiler. Here's the cabin. Here's the coal car. Okay, just like in the movies. Okay, so what's the mass of this thing? It said it's 2.5 times 10 to the 4 kilograms. And we have a thrust. We put a big rocket on here. That's right. Here's our rocket. I'm going to put an Apollo 11 capsule in the coal car, and then, and so the thrust from that is equal to how many newtons? 5 times 10 to the 5 newtons. And it went for how far? 509 meters, so delta x equals 509 meters. And I think it also starts from rest. So we want to find the work done. And then B, the change in kinetic energy. That one's going to be easy. C, find the final kinetic energy of the train if it started from rest. So K final. And then part D, find the final speed of the train. Okay, so let's solve. Now, we're going to say that it kind of says there's no friction in this problem. So yeah, I mean, I got force of gravity holding down, normal force up, and then I have this thrusting force. So this thrusting force is the net force. Okay, so the work done by that net force is equal to that force times delta x times the cosine of the angle between them. Well, that's going to be 5 times 10 to the 5 newtons times 509 meters. Now, the thrust is to the right and the displacement is to the right, so the angle between them is 0, and the cosine of 0 degrees is just 1. So it doesn't affect. So we just go this times this. So the work done is equal to, where's my calculator? Oh, there it is. Five times 10 to the 5 times 509 equals 2.55 times 10 to the 8 joules. That's a lot of joules. That's a lot of energy. Well, you'd expect it. Big numbers here. Now B, now this was the net force, so we want to know the changing. Well, the work done by the kinetic energy the work done by the net force is equal to the change in kinetic energy. Well, this was the net force, so this is just 2.55 times 10 to the 8 joules. It's the same answer. And then part C, well, delta K equals K final minus K initial, right? Ooh, I'm off screen. Sorry. Let me know if I'm off screen, please. Yell, scream at me. Okay, so K final minus K initial. Well, but what is K initial? If the velocity, if it starts from rest, it's 0. 1/2 mv squared is 0, if v is 0. And so this is just going to be equal, and we know that delta, so K final is equal to delta K, which is equal to 2.55 times 10 to the 8 joules. So A, B, and C all have the same answer. Now let's do part D. So K final equals 1/2 mv final squared. So V is equal to 2 times that final kinetic energy divided by the mass, take the square root. So I just solved for V right here. You should know how to do that. And then now I'm going to plug in my values. What the final kinetic energy we found in part C was 2.55 times 10 to the 8 joules divided by the mass, which is 2.5 times 10 to the 4 kilograms. And when you do the arithmetic, you get 143 meters per second. Woot! Goodbye. I'll see you on the next time you're here. All right, that is all.